Welcome to my tutorial on Redox Equilibria. This will be a short introduction. As a starting point, you should have a good understanding of redox equations from your Year 12 content. This will include oxidation states and how to work them out, identification of what has been oxidised or reduced when given an equation, writing simple and complex half equations, combining half equations, and identifying oxidising and reducing agents within an equation. In order to test your knowledge on most of the above, there is an exam question on the next slide. If you pause it, the mark scheme will be shown on the slide afterwards. As this is a 9-mark exam question, it should take you around 9 minutes. There's a small error here. This one should also be worth 1 mark. So let's start by thinking about what you already know from Year 12. First of all, what is a redox reaction? So a redox reaction is a reaction where both oxidation and reduction take place. Oxidation being loss of electrons and reduction being gain of electrons, oil rig. Let's have a consideration of the displacement reaction between zinc and copper sulfate. When zinc, as a solid, reacts with copper sulfate in solution, there is a displacement reaction that takes place whereby zinc will displace the copper from the copper sulfate as it's more reactive than copper, and it will form zinc sulfate. If we consider this in more detail, we can have a look at the oxidation states of the different species within the equations. Zinc has an oxidation state in its element form of 0. Copper has an oxidation state of +2. Remember, when you're doing oxidation states, the sign has to come before the number. On the other side, so your products, copper has an oxidation state of 0 and zinc now has an oxidation state of +2. You can see that zinc has gone from 0 to +2. In other words, it has lost electrons, and when it loses electrons, it has been oxidised. Copper, on the other hand, has gone from +2 to 0. In this example, it has gained electrons. In other words, it has been reduced. We can change the equation into an ionic equation. So you've got zinc in the form of a solid plus Cu2 plus ions, aqueous, plus the sulfate ions, SO4 2-, also aqueous. Those are your reactants. These will go to copper, which is now a solid, zinc, which is now an aqueous ion, and the sulfate ions that are still milling about in the solution. What we can do is we can cancel off the sulfate ions. These are known as spectator ions. And we have zinc solid plus Cu2 plus aqueous going to Cu solid plus Zn2 plus. We can break this down even further into the half equations. For the half equation for zinc, it's Zn solid going to Zn2 plus, and this will be aqueous plus 2 electrons. This is showing oxidation. For the copper, it's Cu2 plus aqueous plus 2 electrons, forming copper solid. This one is showing reduction. What this means with regards to electrons is that zinc has a greater tendency than copper to lose electrons and form zinc ions, and this is because zinc metal is more reactive than copper. The readiness of a metal to give away its electrons to form positive metal ions can be measured as their standard electrode potential. This is the measure that this unit in chemistry is based around. The more reactive a metal is, the more likely it is to give away its electrons to form the positive metal ion, and therefore an electrode potential, standard electrode potential, allows us to put some numbers to this. So my final question on the displacement reaction: why could this be detected as an electrical current? Electrical current is a flow of charge. This can either be electrons in a wire or ions in an electrolyte, e.g. those present in a battery. So what we have here is moving ions and a transfer of electrons. So we have moving charge. That concludes the information for the first introduction video. There is going to be a second introduction video. Before you have a look at that one, look at the 3 displacement reactions at the top of this slide and answer the following questions. Write the symbol equations, make sure you include state symbols, identify the oxidation states of the elements, write the half equations, identify which is oxidation and which is showing reduction, and then identify what the reducing and oxidising agents are.